that should be perfect. Or is it backwards again? It's backwards. Okay. Give me 1 second. OBS. Display capture. Transform. Flip horizontal. All right, good now. All right, so again, like we said in the last video, we're going to focus on review. After the test, we'll, finish up with the remaining content, just so you guys definitely have, the full exposure to the content that you should with this course. But for now, let's just focus on review. And with that in mind, let's jump into one-dimensional kinematics. So, well, that'd be a mistake. Where are we? Here we go. So basically what I'm going to kind of do is go through those old notes real quickly, kind of hit the highlights of them. And especially we're going to focus on, we'll do all the examples in the notes again, just so you guys have those, because those are really good examples. Additionally, I've put, if you haven't logged into AP Classroom in a while, I would do that, because what I've started to do is they've put a list of topics down with a little summary of them. And what I've done is with each section of the topic, I've unlocked questions connected to that topic. Some are multiple choice. There are a couple free response in there. Again, these are not for a grade. We're not taking anything for a grade as of yet. So just kind of, move through them at your own pace, after we do these. I think I might have unlocked like a ridiculous amount of them, but I do as many as you think you need to do. I mean, again, it's not for a grade. This is all you doing what you feel you need to do to be ready. So make sure you do log on to the AP Classroom. I'm also going to send out an email today with a update about how to do that, complete with the codes for each class section. So if you didn't get on before, that's fine. I'm going to send out that info today at some point. But let's jump into kinematics. So when you're talking about kinematics, what you're talking about is the mathematical description of motion. So what you're doing is you're describing motion at its most basic. So you're describing how fast is it moving, how far did it go, how much time did it take for that to happen, did the speed change, right? You're talking about a very, very basic description of how things move, right? There's no reason as to why they're moving, right? That comes with forces when we get into that. It's just your basic, what is this object doing? Again, kina, you see that prefix, it's the Greek for motion, right? So anytime you see kina, you know that it has to do with motion. So kinematics is the study of motion, kinetic energy is the energy of motion, and so on. Now, one thing you do want to make sure that you're able to read, and they're fairly simple. You guys got it pretty much immediately when we first went through this, is your motion diagrams. All right, so your motion diagrams represent the position of an object in, say, 1 second intervals. right? So equally spaced moments in time. So if you were to see this skateboard kid here, right, every second he's traveled the same exact distance. So we know that this motion diagram here indicates that he's moving at a constant speed, right? If you're looking at this athlete, well, notice that every second that elapses, she covers more and more distance. So we know that this person is speeding up, right? If we're looking at this car covers less and less distance every single second. So we know that that car is coming to a stop. So if we were to look at, say, this example, which car is going faster, A or B, assuming there are equal intervals of time between both frame or the frames of both videos, well, car B would be going faster, right? Because it covers a greater distance every single second. Now, again, the way you're generally going to see motion diagrams is a form of the particle model, where we just pretend that we can shrink all of the mass of that object into a single particle, right? So that means you don't have to draw a car, 4 times here. You can just draw a dot, right? That's going to indicate the position of that object. So if we're looking at these three motion diagrams, well, in A, it shows us something that is speeding up, right? Every second of time that elapses, it travels a greater and greater distance. In B, notice that the distance covered every single second is identical. Therefore, we know that it's traveling at a constant velocity. And in C, what do we see? Well, it's covering less and less distance every single second. So we know that this is an object that's slowing down. All right. So again, these motion diagrams, these particle diagrams, are very easy to read. They're fairly, straightforward. You don't really need to know much physics in order to be able to read what's happening there. Keep in mind, right? You got two types of quantities. You got vector, you got scalar. Your vector quantities, those are quantities that have both magnitude and direction. So a good example of that would be velocity, right? Velocity is the object is moving 10 meters per second to the right, right? It gives you a size, it gives you direction. Whereas your scalar quantities, those have magnitude only, right? So what we're talking about when we say magnitude, right? Again, magnitude just means a number that's associated with it. So a good example would be speed, right? The object is moving 10 meters per second. Well, it doesn't give you more than just how fast that object is moving, right? It gives you no direction, so it doesn't give you a full picture, right? So what we deal with in physics is your vector quantities, right? Because your vector quantities give you a more complete picture as far as what's happening there, right? It doesn't just give you how fast it's going, but it also gives you the direction in which it's traveling. So are kinematics, scalar, and vector quantities, right? In kinematics, scalar would be distance and speed, vector would be displacement, velocity, acceleration, right? So your displacement, your velocity, and your acceleration, they all have a direction attached to them. Now, again, keep in mind that there is a distinction between distance and displacement. Often they're the same because the object moves in a straight line, but keep in mind that your distance is how far did the object actually move, whereas your displacement is what's its overall change in position. So in this case, if we're looking at uh, this picture here, let's say this is a kid running. Well, let's say that the path of his run took him down the trail all the way around here, all the way around here, and he reached the end of the trail. Well, the distance that he covered may have been 5 miles. But the displacement, which is what we care about, is how far away from the start did he end. So this displacement right here might simply be a mile and a half, right? So there can be a difference between your distance and your displacement. So keep that in the back of your mind. Right. So again, oftentimes, again, we're dealing with objects traveling in a straight line, so your distance and your displacement are the same, but it is possible for your distance to be greater than your displacement. So here's a good question here. Sarah starts at a positive position along the x-axis. She then undergoes a negative displacement. What's her final position? Well, we don't know. right? It could be either positive, it could be negative, depending on where did she start in the positive position and how great was her negative displacement, right? So if we want to look at that on paper, right? Let's say this is our axis, here's our 0 point. We know that Sarah, and if this is positive, oops, sorry, I don't have an eraser, and this is negative, Sarah starts somewhere in this quadrant. We don't know where. And we know that she undergoes a negative displacement. But again, we don't know the size of that displacement. She could have started here and ended here, in which case she would still be in a positive displacement. Or alternatively, she could have started here and undergone a great negative displacement and ended up here in the negative quadrant. So without more information, we can't determine what her actual position is. And again, I already talked about this, the difference between speed and velocity, right? Speed is just how fast is it going, velocity is how fast is it going plus what direction. Now, one thing also to keep in mind, right? You want to dump out what math has taught you about positives and negatives, right? Positive and negative just indicates a direction. Right? So if we're talking about something moving in a horizontal straight line, if it's moving to the right, it's positive. If it's moving to the left, it's negative. So again, that just indicates direction. Now, if something is moving in uniform motion, and anytime you see that word uniform, right, like when we talk about uniform circular motion, uniform just means consistent, constant, right? So it's moving at a constant speed. So your very basic equation for constant speed is that your velocity, your speed, is equal to your change in position over change in time. Now, again, um, this can only be used when there is constant speed. If the object is changing um, velocities, you can't use this equation. Right? This only applies to things traveling at constant speed. And that's why if you watch any of the waves videos, this equation comes in again because we're dealing with something that is traveling at a constant speed in the form of that energy, that wave traveling through a medium. Um, let's make up a example that doesn't involve uh, miles and such. So let's say you've got yourself a car and it moves a distance of 100 meters in a time of 2 seconds. Well, if we want to know the average speed of that car, your velocity is your change in position over time. I should probably show you my screen. So your velocity would be that 100-meter change in position over 2 seconds. So you have yourself a speed of 50 meters per second. Right? So again, this only is going to be used when you're dealing with objects traveling at a constant speed if you're just trying to find an average speed of an object. Now, what we're primarily going to be dealing with, though, are what we call instantaneous velocities. And your instantaneous velocity is how fast is the object going at that one single moment in time, right? So you're dealing with an object that's changing speeds as it travels. So that's where acceleration comes up. If you have yourself an object that's changing velocity, you have acceleration, right? So by definition, your acceleration is a change in velocity that occurs over time. Now your acceleration, right, is going to be measured in meters per second squared, right? Because meters per second gives you meters per second squared. But also keep in mind that when we're talking about a change in velocity, you're talking about something speeding up, slowing down, or changing directions, right? So if something is changing directions, it still has an acceleration, right? Think back to uniform circular motion, right? You could have something moving at a constant speed in a circle, but it's still accelerated because it's changing changing directions, right? And that acceleration is what we call the centripetal acceleration. So if the velocity changes, acceleration must be present, right? Whether again it's speeding up, slowing down, or changing directions. Again, make sure you know all of your SI units. Um, Also, keep in mind that yes, all motion is relative, right? It's going to depend on the observer itself, right? So You guys can read through that example again, but it's pretty straightforward. If you are traveling as fast as the object you're observing, well, relative to you, that object is stationary, right? But again, most of the time we're dealing with a reference frame that is stationary. But you can always change your frame of reference to make problem solving easier. All right, so this is the big part I do want to hit is graphing. And I'm going to put this document up on, I'll put it up on the website underneath the Kinematics notes, just so you guys have access to this. Because this is a nice little summary of your position time, your velocity time, and your acceleration time graphs. So if we're looking at position versus time graphs, well, there are a few things that you got to remember. When you're looking at these graphs, you always want to think, well, what do your axes tell you? What does your slope tell you? And what does your area tell you, if anything? And look at the units for that. So we know that we've got position in meters up here on the y-axis. You've got time in seconds down here on the x. And if we're looking at our slope, right, your slope is your rise over your run. So your slope would be represented by meters divided by seconds, so meters per second. So your slope of your position time graphs gives you your velocity. So in this case, what we're looking at, you've got a constant slope that's positive. So you have yourself a constant positive velocity. Here you've got a constant slope that's negative, so you're looking at a constant negative velocity. Here you've got a changing slope that's positive, so you have something that is accelerating, it's speeding up. Oops. Here you've got something that is speeding up in the negative. Here you've got something that's slowing down in the positive. Here you got something that's slowing down in the negative. All right, and so if we look at those counterparts in your velocity time, well, you've got a constant positive slope here, right? So you got a constant positive velocity. So constant positive velocity would be represented by, well, a graph that shows a velocity that doesn't change and it's in the positive quadrant. Now, if we're looking at our velocity versus time graphs, again, remember that when we're talking about your graphs, you want to think about what does the slope mean? What does the area mean? So if we're looking at the slope, well, this axis is meters per second. This axis is seconds, so meters per second divided by seconds gives you meters per second squared, which means that the slope here gives us our acceleration. Well, we have a slope of 0, right, because you've got constant velocity, which tells us that our acceleration is 0. Now, one other thing to think about with your velocity time graphs is the area might tell you something here. So if we're looking at the area would be your base times your height. So if we look at our units, right, your base is measured in seconds, your height is measured in meters per second, your seconds cancel, which means your area underneath the curve is measured in meters, right? So that tells you that your your area underneath the curve represents the displacement of that object. That's got to start to focus better. So the area of your velocity time graph represents displacement. This would show something with a constant negative velocity. This would show something that has positive constant acceleration. This shows something that has constant negative acceleration. Again, you got negative acceleration here, and you got positive acceleration here. So you always want to think about what the slopes tell you. All right, lastly, your acceleration versus time graphs, those are very straightforward. If you were to look at the slope of these, that would give you something measured in meters per second cubed. Well, we don't have anything measured in meters per second cubed, so we know that the slope doesn't represent anything useful to us. But if we look at the area, you'd have meters per second squared times seconds, which gives you an area that's measured in meters per second. So you know that the area of these acceleration versus time graphs represents the velocity of the object. So again, I'll put this document up online. It is a nice, handy little cheat sheet for you guys. maybe pull it up when you're answering some of these graphing questions if you run into any issues. All right, so let's say we've got this particle diagram here, right? Well, what does our particle diagram show us? Well, it shows us that this object is moving at a constant velocity, and then its velocity, right, still remains constant for this last bit, but it's a greater constant velocity. So you've got something moving at a small constant velocity, then moving at a great constant velocity. So if we want to know what one of these position versus time graphs represents this diagram here, well, we've got to think about a graph that represents something with a small constant velocity followed by a large constant velocity. Well, this graph shows us something that's not moving, then it teleports, and it's not moving somewhere further away from origin. This shows us something that's moving at a great constant velocity, then moving at a small constant velocity. This represents an object moving at a constant velocity the whole time, so D needs to be your answer. Something with a small constant velocity followed by a large constant velocity. All right, so you're just looking at the steepness of the slope there. And again, if you got any questions, you can always jump in on a chat and ask them. All right, so let's say we've got four objects. They move with velocity versus time graph shown. Which object has the largest displacement between time equals 0 and time equals 2? Again, if we're looking at velocity time graphs, right, we know that the slope represents acceleration. We can use our units to prove that the area represents displacement. So your area under the curve is going to tell you which one of these has the greatest displacement. So you can either solve it out, right? This guy's got 2 meters, 4 meters, 2 meters, 2 times 1.5, 3 meters. So we know that this guy, B, has the largest displacement, right? This one you could just use the eyeball test though, right? Obviously B has the greatest area underneath the curve. All right, so we're given this position versus time graph. And we want to know which one of the velocity time graphs represents that position time graph. But what I would recommend when you're given more complex graphs is just kind of go through it bit by bit, think what's happening. Well, in this section right here, we've got constant velocity, right? Well, the slope is positive, so we know that we have positive constant velocity. It doesn't matter that the object starts with a negative displacement, right? All you're looking at is the sign of the slope. So the sign of the slope is positive here and constant. So we know we need to start with a positive constant velocity. Well, that makes our life easier because only one of these options has that. But let's say you had more than one option that had that. Well, what does this show you right here in terms of position? Well, the slope is decreasing, so the object's slowing down. And then here you've got an object that's not moving, right? It's at rest. Its position does not change. So you've got something that's moving with positive constant velocity. It slows down and the object comes to rest. So again, always look at the slopes. Don't get thrown off by the fact that this object starts with negative displacement. All you care about is what is the sign of this slope here? It's positive and it's constant. That's why we know it's got to be C. And again, remember if something is speeding up, its acceleration is in the same direction as its velocity. And if it's slowing down, its acceleration is opposite the sign of the velocity, right? So speeding up, acceleration and velocity have the same direction. Slowing down, acceleration and velocity have opposite directions. All right, so let's say we've got ourselves an elevator. It's moving downwards. It is slowing down as it approaches the ground floor. We want to know which one of the velocity time graphs best represents the motion of the elevator. All right, so think about your directions. When you're dealing with vertical motion, up is positive, down is negative. So we know that this object is moving downwards and slowing down. So it starts with a great negative velocity, and its velocity decreases until it reaches zero when it reaches the ground floor. Right? So this shows a decrease in your negative velocity, right? Because again, your axis represents zero. So again, you kind of want to differentiate what negative means when you're talking about physics versus math, right? It starts with a great negative velocity, ends at zero. All right, so you got your three major kinematic equations, right? Remember, not the subscript just means initial. So your velocity equals your initial velocity plus acceleration times time. Your final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. And your displacement equals your initial velocity times time plus 1/2 acceleration time squared. All right, so these are your three go-to guys when we're talking about objects that are accelerating. So let's take, for example, we've got ourselves a car. It's got an initial velocity of 15 meters per second. It undergoes a constant acceleration of 6 meters per second. Oops. Squared. And we want to know the final velocity of the car after 18 seconds has elapsed. All right, so those are all of our givens. You got initial velocity, you got acceleration, and you've got time. Well, you look through all three of your kinematic equations, right? It's like almost like a recipe, right? You can only use that recipe if you've got all of the ingredients necessary for it. So the only equation we've got enough info for is that first one, right? Where v equals v naught plus at. So final speed is equal to 15 meters per second plus 6 meters per second squared times 18 seconds. So your final speed is, calculator, 6 times 18 plus 15 is 123 meters per second. And I really need to rewrite that question because that car is really booking it. It's almost going half the speed of sound. And so your one-dimensional kinematics is fairly straightforward. So the last thing we want to hit real quickly is free fall. And when you're talking about free fall, right, you're talking about an object that will always have the same acceleration. So your free fall acceleration is the acceleration due to gravity. Now, again, be careful when you're writing conceptual answers on the AP exam. Do not call the acceleration due to gravity gravity. If you call this variable gravity, you're going to be docked points, right? Because that's not gravity. Gravity is a force. Little g is the acceleration that's present because of that force of gravity. So really be careful about using the correct terminology. I know it's a lot to write out, acceleration due to gravity, but do it because that'll get you the points. Right? So distinguish between gravity and the acceleration due to gravity. And again, on Earth, it's going to be 9.8 meters per second squared. If you ever forget that number for whatever reason, even though we've been using it all year long, remember it is on the constants section of your equation page, which again, I would get familiar with that if you haven't taken a look at it yet. Get familiar with what's on there, what's not on there. So in free fall scenarios, everything falls with the same acceleration, that acceleration due to gravity. And that's because we don't take into account things like air resistance. All right, so think back to those videos I showed you of the feather versus the bowling ball in that giant vacuum room, right? In the absence of air resistance, your feather and your bowling ball, they fall at the same rate and they strike the ground at the same time, right? So mass does not have an effect in free fall, right? Because again, we're always dealing with objects that are with problems that neglect air resistance. Again, keep in mind G varies throughout the solar system. We've seen the equation for determining G on any planet given the mass and the radius. But other than that, you use the same kinematic equations, right? So let's take a look at one last example together. So we're told that John drops a rock down a 12-foot well, and we want to know how long it takes to reach the bottom of the well. All right, so these are the variables we are given. It's a 12-foot well, and we're looking for time. Well, anytime an object is dropped, we can make one assumption. Come on, stop focusing like that. We can assume that your initial velocity is 0. Now, of course, we don't want our distances in feet. So 1 foot is 12 inches. 1 inch is 2.54 centimeters. So let's convert that to meters real quick like. So 12 times 12 times 2.54. So that's 365 centimeters. All right, which is 3.6. We'll just call it 3.66 meters. So you look through your equations. Can I get this thing to stop doing that? There we go. You look through your equations, you see which one you have enough to use. Well, again, you know that any object in free fall has an acceleration of g, 9.8 meters per second squared on Earth. So we could use, right, that third equation. And again, I'm just using y for displacement because it's vertical rather than horizontal. So 3.66 meters is equal to 0 plus 1/2 of g times time squared. So plug everything in. So 3.66 divided by 4.9, take the square root, and you get 0.864 seconds. So again, nothing different from what we were doing with the horizontal one-dimensional. It's just that now you automatically know what your acceleration is because if the object is in a state of free fall, you know the acceleration is that acceleration due to the force of gravity. You guys can find the results on Pluto if you want, where g is 0.7. But we're not gonna. So again, look out for an email today at some point. And try to get on the AP Classroom if you already did register on there, and maybe take a look through some of these questions. Now, again, I did add basically every single question that was available, but again, do as many as you feel comfortable doing. I think it should give you feedback as far as whether you were right or wrong. Right? And so if it gives you a grade, don't worry about it because, again, I'm not taking any of this for a grade. I'll unlock the progress check here probably in the next couple days. I've got to talk to someone about that, about some confidentiality issues. But yeah. So yeah, Monday we'll pick up with two-dimensional kinematics. And again, remember, I've got those office hours, Tuesdays, Thursdays, 2 to 3 on Zoom. So if you got questions about any of those, topic questions on the AP Classroom, that would be a good time to drop in, ask. And if you want me to add a third day, let me know. If maybe Tuesdays work for you, but Thursdays don't, and you'd like to add a third day, I'm fine with that. I can add like a Friday or a Monday or Wednesday. So yeah, email me if you got any questions. I'm signing off. All right, see y'all later.